Namaste, salam, assalamu. Hello friends. Namaste, all of you. Namaste, everyone. And myself, S.S.Takalkar, of course, was Kinetics. Dear friend, I wish you have a relaxation day today. And it is only need if you are kinetic in nature. What it means? The word kinetic means about rate, about velocity, about movement, the science about the velocity. That is kinetic. That means, of course, you must become a kinetic, and for it, you have to do smart work. You have to do exercise. You have to do study and easily work. So here today also we are going to study the new chapter, chemical kinetics. That means it is science which deals with the study of the rate of reactions and the factors affecting the rate of reactions and the mechanism of reaction. Mechanism means during the chemical reaction some bonds are break, some bonds are formed, and there is some intermediate transition states, some energy of activation, some energy changes, etc. All these can be known with the help of this. So some clues, some idea is obtained from the study chemical kinetics. So here chemical kinetics, which deals with the rate of reaction, then factors affecting rate, okay, and the reaction mechanism. Okay. Very important term used here is rate of reaction. What it means? Any reaction taking place, that is reactants converted into the products. For example, if you consider some reactant, hypothetical reactant A giving some current P, right? Now initially suppose the concentration, molar concentration of A is denoted by H, or sometimes denoted by A, moles, number of moles. Initially there is no P, but as the reaction taking place, what happens? Some of the parts converted to here, and its concentration of the reactant decreases. So here A0 becoming A, that is here also written as in terms of A. Suppose X is forms here, then there will be the remaining part. Okay. So this is the concentration after time t. So this is initial concentration and concentration after time, any time, say t. Okay. So X moles of the atoms and A minus X will be remaining concentration, or A simply it is the molar concentration at any instant. Okay. So here in this case what happens? The concentration of A going to decrease and concentration of B going to increase at each moment once the reaction started. Then here again one can say the rate. Let us define the rate of reaction. So we can define it first. Firstly, it is nothing but the rate of change of concentration per unit time. Okay, per unit time, or simply this can be written as dc upon dt. But as you know, rate of change of concentration. So this is the dc dt. So derivative infinite decimal is very small change is considered. If the change is measurable, so it can be written as delta C upon delta T. Okay, suppose 0.2 is the initial concentration or 1 is the initial concentration. Okay, 1 more. Then after some times, after suppose 5 minutes, what happens? There will be 0.8 moles of A. Okay, this is of the concentration of A. Okay, so here, what is the change then? So here, 0.2 moles are changes in 5 minutes. Okay, so here, number of moles per minute. So concentration per unit time is nothing but the change. But at the same time, 0.2 moles of this are formed. Okay, so this is a decrease. So this is a decrease. 0.8 minus this 1 minus 0.8, and this is forms. So the concentration, initial concentration is suppose this, and final concentration is this. A minus A0, so 0.8 minus 1.0, and at the same time the concentration of X increases, so it is the same time 0.2. Okay, consider, look at this now. Now if you consider, therefore the definition can be made more specific. That is the decrease in concentration. Decrease in concentration of reactant or increase in concentration of product per minute time is called as rate of reaction. Rate of reaction. So what is rate of reaction? That is, in short, the rate of reaction denoted by small letter r can be equal to the minus d of Ca upon d. Or this can also be written as minus or plus the change in concentration of this product, say B upon D. Okay, so here this is the concentration, or this can be also minus D of A upon D, or plus the molar concentration of B upon D. Okay, so here the rate of reaction can be defined as the decreasing concentration or increasing concentration of reactant or increasing concentration of product per minute time. Okay, so here now, as you know, what is the time required for the reaction approximately? So it depends upon the particular reaction, because some reactions taking place very fast, within a fraction of second. Some explosive types of the reactions taking place very short times. Okay, or some reaction, for example, takes place for the completion some years also. For example, the fermentation types of them, or the preparation of the wines also required long years. Okay, and the reaction is slow. Okay, so here per unit times, that means it may be per unit second, per unit minute, per minute hours, okay, or per minute day, or per unit years. Okay, so whatever change can be. Now, if you consider this example, consider here the rate is equal to, suppose here at any instant minus sign, if you consider this one upon, okay, then this can be equal to this one. So one can substitute here minus d dt of the rate of change of the concentration at that instant. Okay, this is minus dA upon dt, and this minus into minus plus dx upon dt. Okay, but A is the constant one. A is the constant, and derivative of constant is 0 because A is the initial concentration, and therefore it is 0 plus dx upon dt. So here rate can be equal to dx upon dt. Rate of reaction dx upon dt. Okay. So here we can write R is equal to dx upon dt. Okay. Or also one can write here the rate of reaction is equal to minus dA upon dt or plus dB upon dt, or this can be dx upon dt. Okay. Now consider as this is about the rate of reaction. Now if this is a single reactants, what happens or how you can write the rate of reaction if there are more number of reactants forming any products, because rate of reaction can be expressed in terms of reactant as well as products. If there is a one reactant, two reactants, three reactants, whatever reactants or whatever are the products mentioned. And it is called as instantaneous. Very important. Rate of reaction. Instantaneous. What it means? It means in generally the rate of reaction with respect to particular or given any reactant or reactant or product at that instant. What it means, for example, if you consider example A plus B given product. Okay, so what it means, the rate of the reaction can be. So this is a reactor. So minus its concentration going to decrease. So minus sign is given. Also minus the rate of change of the concentration of B with respect to time. Or also the product may be a C plus B. Or here the concentration of C or B increases, going to increase as the time passes. Therefore, the plus is concentration increases. Therefore, plus sign is given, and plus D of C upon dt, or this can be the rate of change of concentration of B per unit time. Okay. So here the rate of the decrease in the concentration of A with respect to time, or decrease in the concentration of B with respect to time, or increase in the concentration of C with respect to time, or increase in the concentration of D with respect to time. Plus sign, it is not necessary to write the plus signs always. Okay. So here, now suppose this is a single moles of A, moles of B, moles of C. Now if you consider one more example, suppose twice A plus B gives me thrice. Now here one can write here is a 1 mole and 1 mole is reacted with 2 moles of A. So decrease in the concentration of the A is twice the decrease in the concentration of B. Right? Decrease in the concentration of A is twice the decrease in the concentration of B. And at the same time, the increase in the concentration of C, increase in the concentration of C is 3 times more than the decrease in the concentration of B. So decrease or increase is denoted by a negative or positive sign, and the number that is the stoichiometric ratio is here. 2 moles of A reacted with 1 moles of B and with 3 moles of C, or some B may be there. Now in this case, then we write suppose only. Okay, now let us consider this one. Now here, if suppose 10 molecules, 10 moles or molecules, because Avogadro's number of molecules means 1 mole. That is, moles and molecules are only denoted the number. So here, suppose 10 molecules reacted per second. Per second. In 1 second, the B 10 molecules reacted, that means decreases and converted into the product, whatever are the products. At the same time, what it means, there will be 20 moles, double of these. Okay. How many moles are formed with compared to the B? With compared to the B, okay, this is the B. With compared to the B, 1 mole of B gives 3 moles of C. So 1 molecule gives 3 molecules, or 1 mole gives 3 molecules, or 10 molecules gives 30 molecules, or 10 moles gives 30 moles, and at the same time 40 moles or 40 molecules are formed. Then the 1 mole is giving 4 moles, 10 molecules giving 40 molecules per second. Okay. Now, how you write the rate of reaction? How you write the rate of reaction? Consider. So here, if you consider or you compare the decrease in the concentration of B with compared to the decrease in concentration of A, it is a double decrease. Okay. Or this can be, this is the rate of change of the concentration of A with respect to time. Okay, per second. So here this can be written as 2 into 10. This is suppose 10, or this is a 3 into 10, or this is 4 into 10. Okay. So what is this 10? So this is the minimum change in a concentration. That is B, minimum number which undergoes the decrease in concentration of B, or these 10 molecules reacted only. That times twice the A reacted, thrice of C formed, 4 times D formed. Okay. So here the rate of change of concentration of A is twice the. So we can substitute here. What is that? dB upon dt. Okay. Here dB upon dt. That is 3 times dB upon dt, or 4 times dB upon dt. What it means? Now, in fact, this is a decrease, and therefore here minus sign is given. Here is the minus sign. Here, now this is the increase. So here the plus sign is there. Okay, plus sign is there. Plus sign is there. Plus sign is there. Okay. So what it means? The rate of reaction, therefore, rate of reaction may be written as the. How you compare now this one? So this is nothing but the minus dA upon dt is equal to this. This minus sign may be taken to any other side. Okay, can be written as like this. So minus dA upon dt is this. Okay, this, and this is equal to twice the dB upon dt. Therefore, the rate can be written as the dB upon dt is equal to 1/2 times the dA upon dt. Or this can be further written as 1/3 times the rate of dB upon dt, because this is the dC upon dt. Okay, so here dC upon dt. Okay, so rate of change of concentration of the C, that is the increase in the concentration of the C. Okay, only 1/3 is equal to d1, and this is of course the minus sign is there. Okay, minus half of dA upon dt. So one can write here the minus half. Okay, or this can be equal to then here if you consider 1/4 time, okay, minus, because the d of this d, the concentration of d upon d. So here plus, because the concentration increases. Here plus, not necessary to write the plus sign. Okay, you can simply consider that this one. Okay, plus or not necessary. So here, in this case, if you consider one more example, suppose twice of A giving thrice of B giving some product. Generally, higher number of moles are not communicated. Okay. Or suppose here four products or some C. Okay. What it means? So 1/2 of d upon dt is equal to dd upon dt, but decreasing the concentration because these are the reactants, and this is the 1/4 of this. Okay, so whatever. Okay, so all these, and this is the thing, but the rate of reaction. Rate of reaction so can be written in terms or with respect to the reactants or products like this, and this is called as the instantaneous rate of the reaction. So it is with respect to A, with respect to B, with respect to C, and this is very important. Now one can write any. Suppose there is any other reaction. Suppose the rate of reaction depends upon the which factors, what are the factors, second point. So it not necessarily the rate depends upon all and like this, because rate is experimental quantity and we are going to determine, we are going to study it here. Okay, now consider in this case the instantaneous rate of reaction, okay, can be written like this. The rate of reaction may be written like this. Okay, so whatever is the coefficient here, right, it goes to the denominator. Okay, and these are the reactants, so minus sign is there, and first it has a plus sign. Now, we are going to study very important factor, rate law, what is called as rate, okay, equation or law. Okay. So here, they are mostly rate law or also known as rate equation. Rate equation. Okay. Rate equation. So here, let us consider first definition. What it means? It is the expression which relates or give the information or will give the relation. Okay, relates the actual rate. That is, what is? That is experimentally found rate, or the true rate, also known as true rate. True. found true rate or actual rate of reaction of reaction and the concentrations of the reactant. Okay. Which reactants, of course, on which the reaction rate depends. Some reactants are there on which the reaction rate not affected, not depends. That reactants or concentration of that reactants is not included in rate law. For example, if you consider, suppose this is a hypothetical example giving some product, because during writing the rate equation, the product is not considered, only the reactant is considered. Then here the rate law is, so here can be the rate depends upon only a whatever is the power, or rate maybe depends upon here one rate depends different possible depends upon first case one only A only B here on both A and B. A and B. Okay. So here one can write here the rate can be written as or directly proportional to A and B. Sometimes concentration of it, or that is rate is equal to K, or maybe practically. So it is determined practically. During the reaction progress, different data are collected per time. Whatever are the changes per minute time, we are going to solve the problems. Then only it is decided after the experiment, and therefore the reaction rate maybe depends upon it maybe depends upon B, or reaction rate maybe depends on A as well as B. Okay? Again, therefore if it depends upon this, then it can be written as like this, or sometimes the rate maybe depends upon A or B as well. Okay? Now, in a reaction, if there are A number of moles, if there are B number of moles, I give some product. Okay. Then what is about A and B? Suppose A and B are maybe 1, 2, 3, etc. A or B may be equal to 1, 2, 3. Number of coefficients, number of moles of A and B are there. So here A and it may be here A, or it may be a B, or here A and B. But not necessarily A and this A are same. So this can be written as some X, some Y, some X, some Y. What it means? Sometimes that means that is A may be equal to X. B may be equal to Y, or may not be, may not be. This is very important word. So here X and this A may be same or may not be same. This Y may be same or may not be same. For example, if you consider. So here let you know, in rate law, if you consider rate law, okay, for this example, these are the different rate equations. If the rate of this reaction depends upon A, it can be written. If it only depends upon both. Now, if you consider suppose A plus B giving some suppose twice a repeat and twice. Okay. So what is the rate? Rate law. Okay. If rate depends upon a, it may be. Now consider if rate of this reaction depends upon. Consider. Try to understand well about how the rate equations are formed. Of course, rate equations are only formed on the basis of experiment. Experimentally found. Okay, practically found. Okay, so here, what is the true rate? Can be known. Okay, so the rate of the reaction is written, or rate equation can be written, the reaction rate and the concentration of the reactant terms on which, okay, on which reaction rate depends, and the constant and the product reactants on which the rate is not depends. Okay, it is not involved in the rate equation. Now consider here the rate of reaction. Suppose it depends upon A. Okay, so here A twice A. What it means? It means A plus B giving some product. Okay, that is same equation. So how you write here? The rate may be proportional to A, or rate may be proportional to the A into A, or this is one, or rate may be depends like this. Okay, one more of A, or rate may be A into A, that is A square, A square, or one can write like this, simple, or that is A square, and okay. So what it means? How you write the rate law, rate equation? So here one can write here, if practically observe, practically observe. Okay. So here the actual rate or experimental rate or true rate are also known as observed rate of reaction. Now here consider, keep in mind this sentence. Consider. On experiment, it is found that rate only depends upon the A, and again, not the two ones, only one was. So here, the rate equation can be written as rate equal to some K, or in this case, rate equation some constant is square. Okay, and here rate may be A and B, or here rate may be the A square K. Rate of constant. So what is rate constant? Square. Or here in this way. So in this case, if okay. If this is one, or this is one, or this is one, or this is one. Okay. So in this case, this is order, not at all. So it depends upon the practical observation or observability. Okay. Now, in this case, how you define the, so this is the rate equation or rate law. So what is it? So it is the expression. So this is the expression. This is the expression which relates the rate of reaction and the concentration of the reactant, concentration of the reactants on which the actual rate depends. Rate of reaction depends experimentally. Okay, and it is experimentally found. So here it may be this or this. No idea. It is only known about on the experimental observation. Now we are going to study on the basis of very important term, and that is order. Order of reaction. What is that? Order of reaction. So here the order of reaction. So it can be defined as definition. I am going to write here. The number of concentration terms of aqueous reactants involved in rate law. Okay. Number of concentration terms of the reactor which involved in a rate law. Okay. This ratio. Okay. On which reaction rate depends. Okay. On which reaction rate depends. Now here, as you know, if this is the value or this is value 1. So what is the order of this reaction? Of course 1. What is the order of this reaction? Only concentration of A involved. Okay, this is the reactant A, but 2 moles. This power. So this definition is quite modified. Okay, so here the concentration terms of A is involved, but 2 terms are involved. A into A. Concentration of A into concentration of A. Concentration of A into concentration of B. Here A and B both are involved. Here 2 moles. Here are the A into B. Okay. So here definition can also be written as the sum of powers these powers. Okay, this is power. Here of course 1. Here is 1. 1. Okay, 1. 1 is there. Okay, 1. The sum of powers of concentration terms of reactants in rate law occurs at given temperature. What it means given temperature? Because the order of this power can be varied, can be changed as with the temperature. So at a given temperature, which one is applicable? So here, if you consider the rate of reaction, so here, now what is the order? Order of reaction. Okay. What is that order of reaction? Here 1, here 2. Right? Sum of the rate, it is only 1. Here 1 and this 1. 1 plus 1. Here 2 plus 1. So here order of the reaction is 3 means the sum of the powers of the concentration terms in a rate law is 2 plus 1. That is 3. How it is obtained? Of course, it is written on the basis of the experimental observation. It is found that the rate of the reaction depends more this power on the concentration of A and less this power on the concentration of B. Okay, how it is found? So we are going to study the experimental methods to determine order and rate. Okay, order and rate. Okay, so here where yet we know about the order. Okay. Okay, so what is that order? So order can be defined in this way. So order is the number of concentration terms of the reactants. Okay, involved in a rate equation. But if there are these powers are different, okay, here is one, but here is two. Then the sum of the powers, 1 plus 1, 2. So these are the orders. And it is experimentally determined. Because this is experimentally determined. The order of the reaction is depends upon the rate law. Rate. Okay. First rate law or rate equation is written and it is based on the practical observation. And then this order can be determined and not this equation or this rate equation cannot be written on the basis of balanced chemical equation. Okay, because you know here different powers are there. Okay, now this is the total order. This is the total order. Total order. Of course, order with respect to A in this reaction. With respect to A is equal to 1 and with respect to N with respect to B is equal to 0 because B is not involved here. Now consider here. With respect to A, what is that? Order is 2. And with respect to B, what is that? B is not involved here, it's 0. Similarly, order with respect to A in this equation is 1 and B 1. So the given reaction is first order in A and first order in B, or here in this case 2 and B and 1. So here in this reaction the order with respect to A here according to the rate law is 2 and with respect to B is 1. So here total order is given by this way. Now the indivisible order with respect to given reactant and total order is like this. The summation of all the components, reactant components involved in rate equation. So what is the conclusion? Rate equation or rate law, which is based on practical observation, is very important. So you must construct the rate law, okay, for any given experimental data, and then one can find out the order. Now what is about the molecularity? Okay. Now suppose consider the same examples here. The order of the reaction is already written here. The molecularity of this reaction by the definition. Okay, consider. Dear friends, order and molecularity. As you know, if you consider some hypothetical example, suppose A plus B gives some C plus B, or some suppose twice A plus B twice C plus B, or any of the, for example, hydrogen plus iodine for a hydrogen or H2O2 when decomposed giving H2O plus oxygen. So we can balance this. Okay, or some nitrogen pentoxide, okay, giving a H2O2 plus oxygen. So this can be balanced here. Okay. So here, on the basis of stoichiometrically balanced chemical equation, the molecularity can be found. Here, molecularity. The definition is that the number of molecules, not necessarily only the molecules, or atoms also, not atoms of reactants. This is the important one, not the products of nature, reactants. Okay. Is stoichiometric balance chemical reaction or equation. Okay. So here molecularity is the number of molecules or reactants of reactants. Okay. Okay. To this sense. In stoichiometrically balanced chemical equation or chemical reaction. So here it is well known. The reaction should be stoichiometrically balanced. For example, to write hydrogen plus oxygen giving H2O. What is that? This is one way. Or H2 plus O2 giving H2O. Okay. How you balance this? So here O2 is there. Write O2. Okay. Yes. What are hydrogen? Okay. This is the gas. This is the gas. This is the gas. Yes. First formula gas system. Okay. Then it can become a liquid. Here also this is the gas, and this is the liquid. Which one is correct? Stoichiometric balance. What are the rules? So here, generally, half the molecule is not observed, half the electron not observed, half the atom not observed. Molecule may or may not have free existence. Okay, so O2 means what? O2, at least it is one molecule O2 or two molecules O2, but half the molecules. So this is not, and this is not. We consider. So here, on the basis of this equation, what is the molecularity of this reaction? 2 plus 1. 2 plus 1 is equal to 2. This is the molecularity, number of atoms or molecules. Okay, in a balanced, stoichiometrically balanced equation, chemical reaction. And what is the molecularity of here? If you consider here, if you consider this the 1 plus half is equal to 1 and half. Okay, up 3 by 2. Okay, 1.5. Because molecularity is always complete number, integer number. Because molecules not fractional type. Fraction of the molecules not be there, not be stable. Okay. So here it is very simple, so as to write the molecularity. Now, for different examples are there. As you know, suppose we are can be decomposed into water. Okay. Bromine can be decomposed. Okay. Or some examples, nitrogen plus hydrogen giving ammonia. Yes. Okay. So one can balance here. So in the nitrogen, in the hydrogen. Okay. So molecularity of this reaction, okay, can be written. Or one more example are there. Some NO2 here giving NO2 plus here, or sometimes this NO2 here plus here giving NO2 plus here. Let us consider one by one. Molecularity of this reaction, 1 mole is there, 1 mole is there. So here molecularity is 2. Okay? What is reaction? Only reactants. Molecularity is 1. Because 1 molecule is there. Molecularity of these 2 moles are there. molecularity of nitrogen pentoxide undergo. There are molecularity of this reaction gas, gas, gas. Yes, yes, yes. Okay. So here all these are gases. Okay. So here one can this nitrogen. Okay, this nitrogen one is 3. 1 plus 3. Okay, 2 more are already there. 1 plus 1. Yeah. 1 plus 1. Okay. Can you notice here? Okay. No. Next, what is the molecularity in this reaction? Of course, 1. Okay. What is the molecularity of this reaction? This is the 1. This is 1. Okay. So intermediate by 1. So here it will be a 2. So here molecularity by the definition can be written like this. Now what is about the order? Okay. Now what is about the order? Okay. So what is the molecularity? This is the 1 mole. This is the 1 mole. Here 1 plus 1 is equal to. Okay. Now what is about the order? And this is the molecularity. Okay. Molecularity and so here it is not possible to write the order on the basis of balanced chemical equation. For example, if you consider this last example here, nitrogen dioxide and this carbon monoxide giving nitric oxide and carbon monoxide. Okay, this carbon dioxide, it becomes carbon dioxide. So here it is found practically that you must write order or write order or the rate equation is written first, then order can okay, what it means? So rate equation or rate law is depends upon the practical. In this case, it is found that the rate equation, the rate of reaction, only depends upon the concentration of NO2. Where K is the rate constant. Okay, and rate constant is depends upon the temperature, not depends upon the concentration. So here NO2 and CO, here is the first order, and CO is said to be 0. 0 means it is not involved in the rate law. So this rate equation can simply written as the NO2. So this is practically observed. So what it means? It means that even though this is the balanced chemical equation NO2 plus CO, what is that? NO2 plus CO giving NO plus CO2. Okay, this is the equation. Reaction. 1 mole of nitrogen dioxide, 1 mole of carbon monoxide giving nitric oxide and carbon dioxide. But the rate equation is like this. That means the 2 moles of the rate of reaction depends upon the NO2. First thing, rate of reaction depends upon only the NO2 and not on the CO. Not depends. So it is not in or CO is zero. So here that is thus on the basis of this thus order with respect to NO2 is 2 and with respect to CO is 0. So here what happens? The molecularity, but molecularity is okay. What is the molecularity for here? But opposite here 2. Molecularity is 2. 1 plus 1. That is the molecularity is 2. The molecularity is 2. Order is 2. But with respect to CO it is 0 order. Okay. So here, if you consider one more example, or if you consider this example also, H2O2 giving H2O plus O2. Okay. Consider one more example. Decompose. Balance it. 2, 3, twice. So it becomes 4. Twice. Okay. So here, molecularity of this reaction is 2 plus 2. Only 2 moles are there for waste NO2, and molecularity is only determined from the reactants. Okay. But what is about the order? Order. Rate equation is written, and it is found that the rate of this reaction is depends upon this is some rate constant H2O2, but not that these two, but there is only one. What it means? It means the rate of reaction depends upon the H2O2, but not this according to this. The like this. Order is 1. That means if the concentration becomes double, the rate becomes double. Concentration becomes triple, the rate becomes triple. Concentration becomes 4 times, the rate becomes 4 times. Concentration increases, the rate increases in the same proportion. That is the order is 1. So here the order of reaction, therefore order of this reaction with respect to H2 of reaction is equal to and not 2. So here molecularity is 2, order is 1. Consider one more example, the carbon, okay, or some glucose, cane sugar, or glucose. Okay, so this is a glucose, or this is a glucose. Okay. So here, the 1 mole of this cane sugar or sucrose giving hydrolysis into 2 moles. So what is the molecularity? Molecularity is equal to this one plus this one. But what is the order? Order. For order, what is requirement? Rate law. And rate law, order, the rate law or rate equation is the rate only depends upon the concentration of the cane sugar. Okay. So what it means? Thus, it means the molecularity is 2, but therefore order is equal to 1. Okay, only 1 molecule. Okay. So molecularity is 2, order is 1, and not involve this S2 because it is in excess. So its concentration is supposed to be unchanged, or the rate of reaction supposed to be not depends upon the concentration of H2O. If in a reaction one of the reactant is in excess, then the rate of reaction only not depends upon it. Okay. So such a reactions whose the reactions whose in which molecularity and order are different. Order are different are called as pseudo order. Pseudo means untruth. Pseudo order reactions. That means order and molecularity are different. Molecularity is 2. 1 plus 1 molecule. Simple. On the basis of the balanced chemical equation. But practically found that order does not depend upon the H2O concentration, whatever is the H2O, because it is generally excess. And when one of the reactant is in excess, the rate not depends upon such a reactant. So the order is only one. So molecularity is 2, and it is the first order reaction with respect to the sucrose molecule. Okay, first order. Such a reaction is called as a pseudo order reaction. So what are pseudo order reactions? The reactions in which molecularity and order are different. Okay, so this is a pseudo first order reaction. Pseudo first order means what? The molecularity is 2 and the order is different, and it is first order with respect to this. One more example, suppose the hydrolysis of the hydrolysis reaction of methylalonide acetate, methyl acetate hydrolysis reaction. Okay. So what is the molecularity? Of course, count this number of molecules 1 plus 1. But the rate of reaction is only depends upon the concentration of the acetate and not upon the H2O. So here the order is therefore 1. So this becomes again a pseudo order. So here pseudo order, and it is the first order reaction with respect to the methyl acetate. Okay, so here why is the reason very important. Why? Pseudo order taking place. So first means that if one of the reactant is in excess. Okay, let's discuss here. And second, for multi-step reactions. This is very important. Multi-step reactions are very important. If you consider one of the reaction, a typical reaction. So if you declare, so here if one of the reaction is in excess, the order becomes, or reaction becomes pseudo order. This is the number of examples are already discussed. Now consider this example of the pseudo order. And notice here giving you chloride. Okay. And again, this NO2 plus this Cl form again NO2 plus Cl2. As you observe here, what it means? First thing, this Cl and this Cl radical is intermediate. And intermediate always not considered is intermediate, and it is not taken in the law equation. Okay. Do not forget. Keep in mind, whatever is the multi-step reaction, this is a two-step reactions. First step, second step. Okay. This is a slow step. Slow. And this is a fast step. For multi-step reaction, the order of the reaction in output is only determined on the basis of the slow step reaction. Okay. So here, second conclusion. Second one, the order is determined of only slow step. So rate determining step, slow step, and this is nothing but rate determining step. Okay, rate determining step. Rate determining step. Oh, this is one. So what is the order now? So here if you consider NO2 Cl. Okay, this NO2 and undergoing the conformation. Okay, now. Okay. Now consider. Now this is a slow step, and therefore this is a rate determining step, and the order of this reaction. Okay, now consider. So here NO2Cl giving you NO2 plus this Cl and this Cl is there. Okay. So this is the total reaction. There are two moles. Therefore, molecularity of this total reaction. Total reaction. But okay, this is the balanced chemical equation. Finally, we obtain this product and from this reaction. But in practice, this reaction is found to be the first order in NO2Cl, that is a nitrile chloride. Okay, one order is there, so order is equal to 1. So order is 1 and molecularity is 2. So this is the first order pseudo reaction. Okay, pseudo order reaction in NO2Cl nitrile chloride. Okay, so here yet we know about the pseudo order reaction. There are a number of examples also. We can collect it. Okay. The number of examples about the pseudo orders are not important. Just keep in mind the definition of pseudo order, that is the molecularity and orders are different for this reaction, and molecularity and orders not in accordance. The order can be changed because of first thing, the excess order or pseudo order is due to one reactor, and second multi-state reaction. Only rate determining state is slow state. Okay. So further, okay. Now we are going to illustrate the same law, rate law, on the basis of experimental methods to determine the algorithm rate law. Okay. What are experimental methods? First, okay, there are actually two methods. First, consider some example. Hypothetical example. Suppose A and B are the reactants giving some product. Okay, A and B giving some product. Or suppose here P moles or some A moles of A as usual, B moles of B giving some products. In a rate law, only the reactants are involved, so it will not necessary to study out the products. So here, if rate law, it is found that the rate law or rate equation by experiment is found to be this A raised to X and the molar concentration of B is 1. X and Y, what are these? These are nothing but the actual powers, actual number of molecules of X, Y is the actual number of molecules of the concentration in terms of the B, which participated or which is responsible to determine the rate of the active action. So here X maybe X may be equal to A or X may not be equal to A. Also, Y may be equal to B or Y may not be equal to B. That depends upon the practice. Now we are going to calculate X and Y. X is the order with respect to A and Y is the order of the with respect to B. And total order, okay, X is equal to, that is X order with respect to A, and Y, that is the order with respect to B, and total order of reaction is equal to X plus Y. Okay, and this is nothing but the rate equation or rate law. Okay, now there are two methods. Okay, methods. One is the, in this case, the isolation method, and second is the method of initial rate method. Initial rate. What it means? Consider this one by one. Isolation method means if case 1, among these two reactants, one of the reactant becomes excessive. Case 1. One of the reactant taken excess. Say P is taken excess. Then what will be the order? If this reactant is taken excess, then the rate of the reaction only depends upon it. So what is that rate? Rate reaction becomes the A. Now case 2. If A taken excess, therefore rate of the reaction A is taken excess, then the rate not depends upon A, it depends upon B, and then the B with respect to its the Y. Okay. Okay. Now further, when reaction started, as the time passes, okay, the concentration of A and B decreases and product is formed after each 5 minutes or each 1 minute or each 10 minutes depending upon the reaction rate. After regular time intervals, the concentration of A and B are measured. Okay. After regular time intervals, the concentration of A or B measured and B measured and X or Y here. Okay. Now consider now this second type of the method. So dear friends, we are going to stop here today. Thank you very much.